Okay, so next up we're going to be talking about definite integrals, which are a way that we can deal with initial conditions when we're solving separable equations. So I do want to make sure to emphasize that if you find this section confusing, you do not need to use this method. It's just an option for you. But if we wanted to solve IVP for separable equations, I think separable has an A in it. Yes, it does. We can use what's called definite integrals. So they're the ones where you have numbers on the swirly line on the side. And that allows us to include initial conditions from the start. What that means is that you won't be solving for C in step 3, you're actually just going to be evaluating the definite integral. And then just to be super clear, this is optional. Some people find it convenient, but some people really dislike it. So if you see me work through these definite integrals and you say like, oh, having all the variables there is really just too much for me, go ahead and use the solve for C approach. It ends in the same place. It's just good to know if you end up liking this. So we're going to just go back to that same problem we were just working on. Given dt over dt is equal to k times t minus 70, and t of 0 is equal to 300, we want to find big T of little t. And so our approach here is going to be to kind of start by moving everything over the same as we did before. So the setup of these two integrals is the same. But then what we're going to do is we're going to put our variables on the upper bounds. So what's the thing we want to solve for, and the thing it depends on are dependent and independent variables. So that's big T and little t. And then we put initial conditions on lower bounds. But you need to be careful that they match the integral. So this one was about big T, so I put big T over there. And so that means that I have to put the initial condition for big T on that integral, not on the other. So my big T variable is 300 to start, and my little t variable was 0 to start. And then this isn't technically correct the way it's written. A lot of people are happy to solve it this way, and if it doesn't bother you, don't worry. But some people like to use placeholder variables. Wrong place. So in this case, you integrate with respect to s and then plug in t's, and you integrate with respect to u and plug in big T's. You can do whichever version makes sense for you and does not lead to errors. So this placeholder variable is more technically correct, but sometimes it actually causes problems for students. So do whichever one's going to end in the right answer. And then what we're going to do is we're going to evaluate the definite integrals. And solve for whatever variable you need. In this case, it's going to be big T. And so I'm just going to show you how that ends up looking for us. And I'm going to use that placeholder variable version, but in your own notes, if you want to be doing the one that didn't switch, go ahead and do that instead. Sorry, just writing over those equations we want to solve again. So we want to evaluate these two integrals. They're evaluated the same way. We get natural log of u minus 70 on this side and k times s on this side. But now, instead of doing plus a constant, we do evaluated over these bounds. That's how we solve definite integrals. And so it's going to become natural log of big T minus 70 minus natural log of 300 minus 70 is equal to k times t minus k times 0. Do make sure you're plugging in t into the correct thing, especially when we have like parameters hanging around like this. It can be hard to remember where exactly t goes. And I'd like to solve for that big T, so I'm going to have to rearrange things a little bit. I've got natural log of t minus 70 is equal to kt. This goes to 0. And then I can move this natural log of 300 minus 70 to the other side. That's actually 300 minus 70 is 230. So I just went ahead and plugged that in right there. And so then if I apply the exponential to both sides, I'm going to get t minus 70 on the left. So I'm just doing like e to everything. Like that. And now I'm going to go ahead and do my simplifying exponentials. We know that that's e to kt times, e to ln of 230. And then that e and ln cancel out. So this actually becomes e to kt times 230. And so the solution is t equal to 230 e to kt, and then I'm just going to move that 70 over finally, plus 70. And so what's important to note is that if nothing went wrong, this should be the same thing we had before. Here it is. This is the same solution we had before. so we didn't do anything different or special. We end up in the same place, 230 e to kt plus 70, and if we wanted to continue, we would plug in values to solve for k. And it's just a way for us to solve the initial value problem as we integrate without using algebra. Oh, no. Sorry, I turned off my tablet for a second. So these definite integrals do need initial conditions. To work. So if you're trying to find a general solution, you won't have those initial conditions to plug in. You do need to include your constant of integration. But they are helpful if you'd like to avoid the algebra of solving for initial conditions in an initial value problem, and if you can't actually solve that integral, so if you can't evaluate that integral to get to your answer, then being able to set it up with the initial conditions on the bounds is nice, so that you at least have the final solution written in some way. So I'm going to go ahead and pause here so that we can start the next video about scenarios where that might be helpful.